It's an honorary lecture, but it's my honor. And so I'm glad that there was that introduction. And then she saw a few things about Paul. And while I didn't really have a chance to interact extensively with Paul and things some way I feel like maybe I knew him like other people perhaps knew him, right? You read the book about the man-powered airplanes, and you hear the stories and things. So I hope that he would like this one because he was a soaring pilot, and we're going to get into a little bit of that. But doing more with much less, and this is a saying by Paul, and then the last part here, where has it taken me? Because I think, resonate very strongly with that. I'm not going to go into extensive background and things like that. If you have questions about that or other things, but I've been very interested in aviation. I guess I've really worked with that a long time. And as a result, I have a couple of favorite things, right? And I've been pushing. I've had an opportunity to develop my own aircraft. So we'll really be trying to talk about just some of those things, right? And what I think must be most exciting. So this is a SparrowHawk, and I think this is the best handling airplane ever made. Okay? I don't know. That's not really bragging. I really think it is. And people, I look out. I don't think anybody here has had an opportunity to fly one, but it's delightful, okay? And to give a little more information about this plane, that's a 155-pound plane, okay? So as a result, this is dataless. This is the lowest inertia, highest performance combination that's probably ever been made. And so it gives you responsiveness, it gives you feedback, it gives you really exciting characteristics, okay, that are difficult to replicate in other planes. In fact, have perhaps never been done like this, all right? A very interesting combination and very, very nice. I've also done some planes here. It's a big plane, and people probably have seen some of these things. I think there's a chance that this might turn out to be the highest flying airplane, regardless of propulsion, highest flying manned airplane, okay? And it doesn't have a motor. So, now we're hearing more about soaring. First one was a sailplane. This is another sailplane. This is a very interesting plane developed to do dynamic soaring, to fly like an albatross, to fly very fast, to be exceedingly maneuverable. The dynamic soaring requires a very, very difficult combination of strength and speed and agility. Okay, so this is a +11 -9G airplane in the flight envelope. This is meant to be a plane without limits. This plane will break your neck. This plane will punish you with its performance, and that's really exciting in a certain way. Okay, very exciting. That aircraft has been superseded by this one, which I call the Eta Nu. And it's a bit of a different airplane in the sense that, the incorporation of self-launching is a difficult thing, and it has to be sort of built into the plane from the beginning. So here it is shown with a ducted fan, potentially an electric ducted fan, okay? That's not something you can buy, unfortunately, and it's only about half done, etc. But that's how it is. But the name is from the Greek, right? The was, is, and ever shall be. So I think that's interesting. But what would we do, if we have the highest flying plane and the sweetest plane and the fastest, most maneuverable plane? This is that previous sailplane is capable of 225 knots at 24,000 feet. So it's really, really fast, okay, compared to other sailplanes, gruesomely fast. And it can do that and has done those things that I talked about. That's exciting. But what would you do after that? Where would you go? What would be even more satisfying? What would be more rewarding, right? What would be more fun, right? And so this is this next plane, I believe, all right? And I think that's wonderful. And one of the things I've said about it is, and it says right there, how can I fly, right, without leaving awake? Just with beautiful elegance, with flexibility, with rewarding characteristics, with all these things. And so there are some pieces to that, right? And one of the special ones is, 2 seats side by side. And then, the bottom one is, of course, we have to have that performance. And performance expands your experience, right? Performance is fun, all right? And so it comes with a cost. I do understand. It comes with some things. But we have to balance that out. That's what designers do, right? So I guess this is the second experimental electric aircraft symposium. Is that right, Brian? Did I say it wrong? So these are some slides. This was the plane that I was thinking about, and I had even a loft at that point. And an electric airplane, I thought really had some neat, tangibles and intangibles, right? And so I've been thinking about this for a long time. I've been building this plane for a long time. I wish it was done, but I promise you, I wish it was done more than all of you, but hopefully some of you wish it's done too. But it isn't, but it's coming quite far along. And when you make a special plane, what happens is you end up with a lot of very bespoke things. Okay, so it might look conventional, but it's all very special. That's the real plane. That's a molded, pre-preg carbon fiber plane. So the mold's been made. The propeller's special. We won't talk specifically about it, but it's very integral to the whole plane and its performance. And that's a special propeller, custom made, custom designed for this. And it, in general, looks like you see here. Okay. Long wings, I guess, for some people. For some, maybe not so long. But a plane that weighs about, 1,200 pounds gross. We're going to talk a lot about 900 pounds in this discussion, just because that's kind of a weight for a single person. And, as an electric airplane, it suffers from some great deficiencies, right? It can't carry much energy along with it. So we have to be very efficient in everything that we do with it. And, meaning, i.e. very clean, right? We can't have a lot of drag. The propulsion system has to be terribly efficient also, so this tractor configuration is a very good way to do that. It's integrated into the airplane. Otherwise, the conventional airplane, I believe, right, you looked at the previous planes that go the highest and, have the highest lift-to-drag ratio. I didn't say it, but an A to Nu has about a 52-to-1 glide ratio, and that holds up, very well throughout the speed range. So that number oftentimes talks about a peak number, okay, which I consider almost irrelevant, but what does that performance, look like? So I do know there's some soaring people here, and this is called a glide polar, and it's really just a measure of sink rate, and it's for straight line flight, and oftentimes we're circling, and we'll, in the analysis later, we'll include circling, and I may not specifically point that out later, that this is not necessarily directly representative of that. But it is the one that you see when you talk about gliders, and then when they talk about glider performance, they'll talk about this polar. The glider people will get right on this and talk about the polar. So at varying speeds, we have varying sink rates, and in general, as you go faster, the sink rate increases. Okay, we see that out here. At the higher speeds, 120 knots, the sink rate, and these are quite low, I guess, in the whole scheme of things, but 500 feet, right? So it's coming down at 500 feet per minute at 107 knots forward speed, right? There's some things about these polars that change with altitude. Reynolds numbers changes, other things happen, but, this is a sea level polar for that plane, the Goshawk, okay? The 2-seat side-by-side plane, you might call it a motor glider, at 900 pounds. Here we get into this stall, and this is this drop-off. That's where you're really getting draggy, and the sink rate starts increasing again. But we can change this into a little bit different format, where we just sort of convert it into lift-to-drag ratio. So this is for the same vehicle. Those are representative. We have speed, and then we have this lift-to-drag ratio, which at high values of lift-to-drag ratio equates to sort of this glide angle, if we go back to some kind of soaring thing. The Goshawk then has a peak number that's pretty high, and that's very damn good for a fixed gear airplane, right? And I should just comment too, this particular polar is not including the feathered propeller, but sort of removes it for the sake of this analysis, like it's operating in a propulsion sense. And when we do operate in a propulsion sense, I do account for this slipstream and the extra weight from that, the accelerated air, that comes out of that prop disc. So it's an electric airplane, and I would like to compare it with some other things, electric vehicles, and we'll just use some ground vehicles, right? And we want to characterize a couple of vehicles. I picked a couple of Teslas here, and we go back to this lift-to-drag ratio, and we can think about the lift-to-drag ratio for a wheeled vehicle, all right? And so I've eliminated the lift-to-drag ratio at zero velocity, all right? It's an uninteresting point, actually, and there's some peculiarities that happen there. I guess I did show this slide to someone, and they asked, where did you get this? And I said, well, there's enough information about some of these cars. They've put them on dynos, they've done some other things, and so I can infer a lot of things, and I can peg down a couple of points. So I've put all the pieces in there, and it matches up quite well with the predicted performance of the plane, like the predicted performance of the car, like their top speed and some of these other elements, right? That previous set of data, the lift-to-drag ratio, can then be converted into this other one, nautical miles per kilowatt hour, right? And forgive the units, but I just decided that we would use nautical miles, knots, nautical miles per hour, knots, and then of course we have kilowatt hours. Kilowatt hours, is, right, that's distance divided by energy. So just think about the units that way and you won't get too confused. But you can see that the Goshawk is very much more efficient. Now, they're completely different vehicles. And I did actually, the information for the Teslas is for single occupant, and the information for the Goshawk is for single occupant. So, you could put more occupants in it, and they're a little bit different. But let's just, for fun, we'll put something really extreme in there and see how that compares with the Goshawk. Because the Goshawk obviously was much better at covering distance for a certain amount of energy than those two wheeled cars, right? Very nice cars, though. This is a specialized vehicle that is the previous presentation had the Sun Racer, right? This is a new class now that the Sun Racer competed in that race across Australia, and now they have a different class called the Cruiser class, where they reward some points for some extra amenities like extra seats. This is a 5-seat vehicle. It did race across Australia, and it averaged 22 nautical miles per kilowatt hour. It also did that with an average number of 3.4 occupants. And so I have a curve for the vehicle with a single occupant that I've derived, and then we can see the big green dot over there. So while that's very much better, it only does it at maybe even perhaps an uninteresting speed, right? It's not better than a Goshawk below 60 knots, right? So the plane is very efficient at these higher speeds. And I'm not sure if, maybe this speed right here, this average speed of 37, maybe that's not even terribly interesting for you. Might be too slow. Let me just check. I'm reading the slide here. The lift-to-drag ratio at that low speed is quite high, but that's important if that's the speed you're going, right? If the competition eventually goes this much faster, maybe they'll have to get those wheels off the ground. The Goshawk utilizes all the components from the Zero motorcycle. So the battery is here, the motor's here, the controller's here. So I threw in this extra slide here. What if we put a Zero motorcycle, which is an electric motorcycle? I think, I didn't actually say it, but that's that purple line. Okay? So not as good as the Stella V, very good, much better than the car. And I think one of the other slides earlier in the day had a motorcycle in there too, and was talking about, and I can't quite remember whose it was, but it was in there. All right. Now we take this, and the reason I presented that is to say, here's a Goshawk. It's a very efficient vehicle. Maybe we can all even agree on that. And so it's an electric vehicle. It's as efficient as we can do, right? The whole design is built on this efficiency. If I was going to now show you some kind of performance curves for something else, right? Like a business jet in this case, this is some plane. You can see this graph. We're talking about taking off. We're talking about climbing over the airport. Then we start a climb in the direction of our destination, and we cruise, and we come and descend. So we have, 1,152 nautical miles, burns 191 gallons. It does it, up here at the cruise at 422 knots, and it takes 8.4 minutes and 14 gallons to climb to 28,000 feet. Sorry, that one's misplaced, but that little arrow is supposed to point to that corner up there. The little gap in there I didn't graph, but that's the acceleration from the climb speed to the cruise speed and some other things. So a lot of stuff's built into this, and it's the same analysis that then I'm going to show for the Goshawk. And this is where it's going to get disappointing. Okay? So we went from 1,100 nautical miles to 191 nautical miles, right? I noticed that some of the other graphs talking about range and other things are talking about weight fractions of 50% for the batteries. Wow, that sounds really good, okay? I think it's quite unachievable. But the Goshawk has about a 190-pound battery pack, and so in this case, 190 pounds over 190, you can do that weight fraction for yourself. Whoops. Sorry about that. I went to push the laser and got the next slide. I'm only climbing to 2,000 feet. That takes not too many minutes, but it consumes a big fraction of my 14.4 kilowatt hour battery pack. I can cruise along at its best range speed, 65 knots, not terribly fast. At that point, I'm getting 16 nautical miles per kilowatt hour, which is very much more than the Teslas can do, very much more than the Stella can do at that speed. I can do that for about 2.7 hours, and then I can descend and then do this. So this is kind of a range profile for things. And maybe you're not excited about it, right? But it's still very good, I think, right? One of the really nice things about having a little battery is it doesn't turn out to be terribly expensive. All right, so the plane, though, is really efficient. And as a result, it also can turn out to be quite fast. This plane will go 172 knots. It's structurally capable of that. You see the same climb. You see the very high-speed cruise. That consumes the battery very rapidly. The range goes down to, just under 73 nautical miles using the same 14 kilowatt hours out of the 14.4 kilowatt hour pack. All right. Average speed, though, from across that is 157 knots. That's kind of fun. Soaring. So, soaring is something that's very exciting. Soaring is something that's rewarding. I enjoy it very much. And we're going to talk about incorporating that now into elements of this electric flight. Right. Ultimately, regenerative soaring will show up, and so we're going to take energy from the atmosphere. We're going to fly in the updrafts, and we're going to avoid the downdrafts. We're going to do those kinds of things. And then just to point out one thing, conventional soaring only stores energy in the vehicle with potential energy, with altitude. All right. Hopefully, people have a little bit of understanding. We're going to talk about thermals and thermaling. All right. That means you circle in the rising air, thereby bringing your vehicle to a new altitude that's higher, adding potential energy to the system. You then glide over to another column of rising air, and you repeat that process. And gliders can fly for many, 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 many hundreds of miles, right? 1,000 kilometers is one of the big achievements that you do in soaring, and the planes there have done that. Well, not the high altitude one. But even the little SparrowHawk has gone 1,200 nautical miles on a soaring flight. So 1,200 kilometers, right, which is quite a long distance. How do you get these unpowered vehicles going? If you're not familiar with another soaring term, aero towing is what you do. You hook it up, and I hope everyone kind of says, this seems silly, but it's what happens. I put that one picture in there. Siemens put an electric motor in a plane, and they did tow a glider. They called it the first time that's ever happened. If they were here, I'd ask them how many kilowatt hours they used to do that tow. Do you know? 16. Wow. Well, that's because that plane in the front is really crappy. But But here's a regular plane, all right? And we can convert the energy capacity in gasoline. There's conversions, there's efficiencies, there's other things that might happen. But I estimate that about 40 to 80 kilowatt hours in gasoline is used to do a tow, right, in a conventional tow plane. And right, one kind of plane is not used, across the board, but Cub-type planes are used. Pawnees are terribly draggy things. They're kind of a Cub with the wing on the bottom, but you can use Cessnas and other things to do this towing operation. So when we get back to the soaring, and we think about soaring, we say it's completely free. It's not completely free because we make an investment in the beginning. Okay, that's this tow. Another little graph, because we're going to talk more and more about soaring, but it's a little figure, and I think it's quite nice. And one of the things that we're going to talk about here is, that when you do your Tesla, you can accelerate, you can recup some of that energy. You pay a heavy tax on that because you don't get it all back. And then none of the parts of this regenerative soaring that we're going to get into are terribly efficient either. But what we have, though, is we have the ability to sort of go downhill for as long as we want. And that's when we stay under these clouds. And oftentimes the thermals are marked by these cumulus clouds. And this figure shows those. And hopefully you'll see in these next figures here what that might look like. Okay, from the ground it looks like this. These are called cloud streets. This is a satellite picture. You can see all the white dots. Those are clouds all over the place. This is a 270 nautical mile, or in the soaring world, a classic 500-kilometer triangle, right? What's the reason for this? To say that it is possible to have clouds all over the place and to cover distances and do it. Maybe not every day. If it's a bad day, you get stuck doing those other range profiles. But if it's a good day, you have some new options, some new exciting options. Look at this. You could go a very long distance here in a sailplane. But in a goshawk, you can also then have a really interesting opportunity to recharge, right? Recharge your battery. So rather than just storing energy in altitude, right, we get to put it in a box. Okay? And that's kind of exciting. Another glide polar, just like the previous one, but I've included some regeneration points. Now it looks like those lines are all parallel, and it turns out they're not. But because the efficiencies in the propeller works pretty good, not good, not perfectly good, but its changes across this speed range and stuff are relatively small. So while those lines look parallel, they're not exactly parallel. But we can see that the extra sync rate that you would incur from a 1 kilowatt regeneration, a 2 kilowatt regeneration, or a 3 kilowatt regeneration here, it's increasing your sync rate. Okay? I asked Peter, he's going to keep me honest whether any of these cases are possible. Do you think that you could fly this plane in 3 knots of lift? And that's not what you achieve. That's the lift in the thermal. Peter nodded. How about 4 knots? 4 knots of lift? Can you do that ever? Do you see that conditions? 5 knots of lift? If you can do 5 knots of lift, you can recharge in 34 minutes. All the energy that you used to launch that plane. Okay? So now I'm going to make a bold conclusion that flight without recharging is easy, which is really exciting, right? To fly this plane now, to fly an electric airplane and never recharge. That on most days, okay, you could come back with your battery full. And so that's not just doing something down here at the bottom. This might be approaching doing more with very little to nothing. So not just much less, but almost nothing. And that's what I like to think about. This is a wakeless flying. This is something really exciting. This is something super satisfying. So, and if it's not your gig, we can even talk about a new way to do it. So now we have this propulsion system. We're using it to take off. We're using it to climb. We're using it to get started in our soaring. Is there another way that we can use it to help us have even more flexibility, maybe even more performance? Okay, we can use this propeller in the front to regenerate, so we can visualize it like one of those wind turbines you see spinning in the wind, and we can put that energy that we use to take off, we can put it back in the box, and we can take it home. We can use it again when we want it. But we can also use this propulsion system to change the performance of the airplane, which gliders don't really have to do. Sometimes on the ground, they'll change their weight, and that'll affect the glide polar. But we can now use it to aid the progress of the plane. So we're going to take one step back. We're going to look at this glide polar again, all right? And then this is a conventional motor glider. Someone might say, a Goshawk is just like this plane, okay? In fact, it's very much better than that plane, even if we just feather the propeller. And so the previous picture designates a certain plane. That plane is characterized by this performance, this sink rate versus airspeed curve. The Goshawk is much better. We can take our propulsion system now, and we can add a little bit. So rather than those range profiles that we were talking about previously, where we were flying in level flight, okay, which would mean we're adding enough power that we don't have any sink rate, okay, we can add 1 kilowatt to the plane and improve its performance. We can add 2 kilowatts. We can add 3 kilowatts to the plane. It still won't quite fly in level flight, okay, but its sink rate versus speed gets a lot better. And this will be important now as we start to compare it to much more high-performance airplanes. This is a single-seat, 15-meter standard class sailplane. It has a sink rate versus airspeed curve that looks like this. The Goshawk's still better than it, maybe not quite down here at the low-speed engine, some of the climbing cases, but if we put 1 kilowatt in, it's dramatically better than that airplane. And so we could fly putting 1 kilowatt out the shaft, right, for hours and hours and hours and hours and hours, 11 hours after our climb to altitude and getting started in our soaring. Here's a high-performance 15-meter plane, right? Again, that's that plane that was pictured. Now we're really, looking at a plane that's better than the Goshawk. But if we put 1 kilowatt in the shaft, Goshawk is very much better than that plane. One of the things that the planes use, and I did allude to it briefly about changing the weight, is you can add weight to these planes. It moves that glide polar, shifts it, the sink rate increases, but the speed at which those sink rates occur move out to a higher speed, changes that. So we look here, okay, and so 1 kilowatt in, but at the higher speeds, but we can put 2 kilowatts in and match it all the way out to quite a high running speed of 115 knots. This plane has a 100-foot wingspan, 101-foot wingspan. Maybe you've heard about it. It's called the Ada, and it's very expensive, right? In some ways, it's starting to be comparable, right? We went from single-seaters to now a two-seater, but they sit in line with each other. It is a self-launching plane. It's not an electric airplane. Very high glide ratio, right? In the high 60s, perhaps, right? Maybe 70 or something. In contests, this plane didn't turn out to be very much better than some of the smaller wingspan two-seat or open-class airplanes even. But still, we see that 1 kilowatt in the shaft brings it up. 2 kilowatts makes it better than the Ada, right? Here's something that might be more comparable again. The Stemme S10, it's a two-seat side-by-side self-launching sailplane. Okay? Goshawk with a little bit of power, very much better. And I do have 2 curves on there for different weights on the Stemme. That's probably a bit optimistic. Even that company would admit that probably doesn't perform with some of the published glide polars for it. This is an electric self-launching sailplane, the Antares. In some sense, that's very comparable, okay? And I would say that, it isn't necessarily my style to compare against other manufacturers' vehicles, right? I have a picture of a plane sitting on the ground, and I have pictures of their planes flying. So, but still, let's see how we might compare against this airplane, which is a very high-performance single-seater, and is an electric self-launching sailplane. So in some ways, they're getting to be quite similar. If we add a little power again, we can compete very favorably with a plane like that Antares, all right? And one thing about the configuration, and I'll go back if I can, please. It's an electric self-launching sailplane, but oftentimes in order to maintain their very high performance, they utilize a system like this, where the motor is on a pylon and then is retractable into the airplane. So when they're in their soaring mode, they look like those other sailplanes. You don't see any evidence of that propulsion system. That, though, precludes its use as, it really precludes its use as an effective regeneration tool, okay? Where we can windmill that propeller, put energy back in the box, back in the battery. So it doesn't have that complete flexibility because also it's mounted on the pylon. It's quite draggy, so it's not really effective to use as a performance aid, okay? In fact, that's so draggy, it's akin to having the air brakes open when that's deployed, so they really waste a lot of their precious battery energy. We have a representative here, or a couple from Pipistrel. Here's a plane that's getting closer again. It's side by side. They have an electric self-launching option. Its performance maybe is arguable, plus or minus, but we can see that we think that the Goshawk might be a very good soaring plane. And if you start adding, extra thrust from the propulsion system, it really, really gets quite good. Okay, now, if we really dig into this and we really start accounting for, the regeneration, the actual efficiencies of those things, cross-country flight, thermals, thermal profiles, thermal strengths, okay? So we'll distill that down into just 3 cases, all right? Good, medium, and poor, all right? And what happens when the conditions are really poor in a sailplane is that you will not make it to the next source of lift. You will land out, all right? And but in strong conditions, right? And now here we're looking at the Ada Nu. We saw a picture of that earlier. I would say I'm going to make a bold claim. This is probably the highest performance sailplane, regardless of wingspan, ever made. You can see that in good conditions. And again, I'm not presenting all the details of those thermals and their diameters and their strengths and everything else. But, and here we're playing this trick again with weight, right? And I'm going to include this, but very high average speeds. This is an average speed, okay? So it can do over 100 knots for hundreds of miles, right? Which might be faster than your 152 can do, even with its motor running. The SparrowHawk, we saw a picture of that. That plane's, very good in some conditions. In very strong conditions, it suffers against this very high-performance airplane. I put this one in just as a comparison, so, you might say that's not a lot, but in the competition world, this wins every time, okay? 103 knots beats 98 knots every day, and the points will just add up, and you end up with a crushing victory. The Goshawk now, all right? Now we have a complicated situation here. We're going to present a couple of cases. And this idea of regenerative soaring is really exciting because it's exceedingly complicated, right? So you have flexibility, which is easy to think about. I'm in trouble, I'll use the motor, which is a really nice thing. You cannot underestimate that. But if you were really trying to optimize it, how would you do it? And so I've discretized that a bit. And so in strong conditions, right, you just have to, and then we'll go through this. Without regeneration, okay, if you feather the propeller, you can go 62 knots, okay? If we put 1 kilowatt in the shaft, right, we can go 79 knots. If we put 2 in and 3, 113. So now we're very, very much faster, all right? Even if you run 3 kilowatts into the shaft and you never regenerate anything, not your takeoff or all of the hours spent, and this is a 500K flight, so it's 270 nautical miles, you still won't use all of your battery. You only use 10.9 kilowatt hours of it. So by not flying level, by soaring a little bit, we're really, remember we could only go 190 nautical miles at 65 knots, but now we're going 270 nautical miles at 113 knots, all right? That's that. All right? Remember, the fastest conventional sailplane was only 103 knots. We'll add another case here. This is where we're going to regenerate the takeoff energy, right? And, of course, that regeneration slows your average speed down greatly. Still not too bad. This is what's kind of exciting. it's still faster than flying with a feathered propeller. So you're paying a lot of tax, you're getting these other intangible benefits, like I'm in trouble, I'll use my motor. But we're recuperating our takeoff energy here, and it's still better than not using regeneration, right? So that's really neat. If we regenerate the full load, everything we use, every time we use it for propulsion, we're going to get that energy back. Every time, the takeoff, we're going to get that back. So this is landing again with a full tank. And so it really does dig into your speeds, but entirely possible, right? You can do a 500K flight and land with your tank full. And I think that's unbelievably exciting, unbelievable, satisfying, rewarding, all those things I was looking for in the beginning. I think this is how, you can do that. Medium conditions now, we'll go through this a little quicker. The speeds have come down, you see, all right? The regeneration takes a little longer. You take a bigger hit. Without regenerating, you can still go very fast. Now the Goshawk goes very much faster than the other planes. We can, if we wanted to put the 3 kilowatts in, we can do 70 knots, which is better than the fastest of the conventional airplanes, and not just by a little, but by a lot. Remember that this plane is just designed to excel in those good conditions, to go as fast as any sailplane could. But now, if you don't want to recharge, you can be the fastest plane flying that day, at least amongst the soaring pilots. Okay. The Goshawk, again, if you want to charge up, it's digging into that, and we can still do that. We can land with a full battery. I hope this now can draw one of the things that's flexible about this plane, where it's really adding, right? Anytime, anywhere, how can I have a good time? And this is when you have a bad day, because now I went to, I think. So on a bad day, you can see that the sailplanes really slow down, okay? And I can tell you that the Germans can't make a plane that light to fly at 500 pounds, 15-meter plane. I can. You can see the 1,100-pound plane lands out. The heavier AeroDynamics land out. The SparrowHawk, which is quite excels in light conditions, it makes it around. The light AeroDynamics makes it around. The light ASW-27 makes it around the course. But the Goshawk, of course, with its ability to enhance its performance, right? If you feather the propeller, you're going to land out. If you fly with only 1 kilowatt, you're going to land out. But if you start to add a little more, right, you get to keep going, and you get to have a good time, and you can still do a 500K flight on a day when the other sailplanes are landing out. That's unbelievable. It's really exciting. Of course, if you're landing out, you can't recharge. But even if you do, right, you can still make it around. This is an unreasonably slow speed, though. That you can't do 500K at 6 knots. It just takes more than a day. But you saw on the previous slide, you can make it around at a very nice speed. Okay, and then we go to the last one where you're charging up everything. Of course, the speeds are low, so they're still low. So that's pretty fun. This is one that, I'm not sure I'll read all those things. I think you might find them interesting. There's some little points about the plane, right? What's the best climb rate, what it might use, what's going in, what's coming out of the shaft. Go ahead and look at that. Maybe you want to look at that one. It's like the world's most efficient propeller. 85% might be a little high for an average, including takeoff and cruise. Although this one's 80% in climb. Some more points, some extra little points with power enhanced gliding, right? Power enhanced cruising, not level flight, but some other things. Here's the maximum speed. 174 indicated, almost 200 knots true at 8,000 feet. So it's very fast. And that's really just a function of clean. So it's going 200 knots with 37 kilowatts into the prop, which is whatever, 42 horsepower or something. Not exactly sure. One of the big tough design points for this plane, though, was to have a propeller that would work in this exceedingly low power environment, also work in that climb case. You just don't have any energy to waste. And so some of these fast glides, it's interesting. You're really going to have to have a constant speed propeller, right? Turn it down to 700 prop RPM. The propeller efficiencies can still be quite high. They don't really like to have so little power put into them. The blade angles get quite high, right? And so some of those, if there are airplane people here, they might find that interesting. The designers. I'll just pop back and in the previous slides I didn't really compare to the Ada Nu. This is the Ada Nu. This is the glide polar at 2 of the weights. Okay, and this is a bit of a review in a sense. And I know that maybe the soaring thing's not interesting, but this is what happens when you add weight to the plane. 750 pounds, it's lighter, it goes slower, right? The sink rate's lower. 950 pounds, sink rate's higher, but those speeds are pushed out. And so when you're in strong conditions, this is why those heavier planes tend to work better, right? You spend less time climbing, more time gliding, and so overall you go faster when you're heavier. A bit of an explanation for that. Overlaid then the Goshawk and the Goshawk with power assist on what I believe to be the very, very high performance Ada Nu. And then that's that one there. So, a Goshawk does have a chance in certain situations. And if you don't really want to land with your battery full, you can race around with that plane. So for me, this electric plane, this regeneration, these other things, to me it's a means to an end to accomplish what I then believe is, one of those other corners of what can absolutely be the most exciting, the most rewarding, the one of the ways to have the most flexibility, to fly in different conditions, I just think landing with the battery full is just going to be the most fun thing you could possibly do. How long does it take to charge up? I don't know. I never charged up. I flew all last summer and I never charged up. So, hopefully, I took the, I pushed the discretion, of course, to talk about soaring, to incorporate soaring terminology and other things. But, if you didn't know anything about that, I hope you learned something. If you did, I hope you found it really interesting. Are there any questions?
I really found this amazing that such a small amount of kilowatts made such a big difference. And of course, it immediately makes me think of these flexible solar panels from Alta Devices, that if you have enough area on the wing and tail of the Goshawk, that you would, get a continuous 2 kilowatts for free on a sunny day. Have you done any looking at what a solar energy system would do for that airplane?
This is a common question, I think, and that doesn't mean it's a bad question. It's just one of the ideas, one of the founding concepts on the plane in order to get high performance is that it has just the minimum amount of wetted area possible, which means it doesn't have a lot of places to put solar panels. It incorporates very high performance airfoils that require a lot of natural laminar flow, which is perturbed by the contour deviations, the ripples, the other things that the solar panels often bring with them. Right? My experience with the solar panels is that I have a solar panel on top of my SparrowHawk, and it won't run my electric instruments. It just sort of helps. Now, I'm all into helping, and I think one of the most interesting things about when you're efficient, right, then a little bit is a measurable help. And if you're not efficient, then a little bit is just nothing. So it's difficult to make a solar airplane, and it's difficult to make a solar airplane fly level. You see the solar impulse, okay? I don't think that's an interesting airplane. I'm not interested in it at all. I don't like a plane that loses control when it exceeds a 10-degree bank angle and will crash, okay? That's fragile, that can't fly, that can't be out in the elements. But I think there are really exciting things for the solar cells, to put a battery in your trailer and to charge up, or to put a battery next to in your hangar, and have some solar cells on the ceiling and things. And I think in the whole scheme of things, my interpretation of that is that they should be left somewhere else, and that the Goshawk then should be performing as best it can. And the regeneration thing, the power in the thermals is much, much, much more than you would get from the solar cells.